Thank you, everybody, for joining again. So this is the continuation of our discussion a couple of weeks ago, where we were talking about the Spitfire QoS. So we'll continue that discussion, but before we move forward, actually just a quick recap what we discussed. And we do have the recording available, and we'll come back to that recording and the pointer for the recording later on. But we talked about what feature is supported, what's not supported. We talked about in great detail the VOQ architecture, how it works, the credit grant, credit request, credit grant mechanism, and the protocol, how it works. Then we talked about the priority queuing or priority classes. Out of 8, P1, P2 are the priority classes. P1 is a higher priority than P2. Then you have the normal priority classes as well. We talked about the egress queuing, which is based on the traffic class. We'll touch upon that one again today. We talked about the egress marking, which is matching, based on the matching on the QoS group. Ingress policing. Policing is only supported on the ingress side, not on the egress side. We can do the ingress marking. We can set the QoS group on the ingress side. We can set the traffic class for the queuing behavior. So if we are applying a QoS policy on the egress such that it has the queuing behavior, that is based on the traffic class on the ingress side. And then we talked about the memories, HBM high bandwidth memory versus the SMS shared memory system, and the limitation of the SMS and how and why the queuing or VOQs migrated from or evicted from SMS to HBM and during the congestion and all. So we talked about that in detail. We'll continue on top of that. And some of the things we probably will have to quickly revisit that if the time permits. So continuation of the VOQ architecture, we talked about that. We have the ingress port here, P10, P20, and an egress port, P00 or port 0. So we have a scheduler on the egress side. We talked about that one as well. On the egress side, the scheduler is being shared in an interface group. So on the ingress side, we have the VOQs for each outgoing interface or each egress interface. In our case, it's port 0. And these are the queues, ingress queues or the VOQs for this particular port on NPU 0 and NPU 1, let's call it that, right? And then we have the mechanism of requesting the credit once we have the packet in the ingress queues. And we have the ingress scheduler, egress scheduler, and then we have the credit grant protocol run between them. And then we have the BSC, the mechanism which actually provides the credit to the ingress side. So if we take this policy, how it works on the ingress side, so we have a policy applied on an ingress interface here. Keep in mind that we have the traffic classes from 0 to 7, and then we have a base VOQ, which we will look into the router as well today. And then we have the VOQ offset. So VOQ ID is base VOQ plus the VOQ offset for each VOQ queue. And if we have this policy applied on the ingress side, so this policy input ingress policy, this is the policy where we are setting the traffic class in each class within the class map or within the policy map. So these classes are matching in the DHCP values. So as the name suggests, DHCP 7 is matched on the DHCP value 7, and then we are setting the traffic class. So this is a very simple QoS policy, and then we are applying it on the ingress side. So how it works out, let's see. So when the traffic comes in, we have what we are seeing here is the green, blue, kind of orange, and then maroon color. So these are the queues with the traffic. So these queues have the packets in the queue. So as we know that the VOQ 7 is the highest priority queue, which is a P1 and then P2, and then these are the normal priority classes along with the default class. So first of all, the most high priority queue will be serviced. So we'll see how that works out. But if you look at the show policy map interface command, it shows us that we have the incoming traffic on these queues. So DHCP 7, DHCP 6, DHCP 5, and then we have that default class. And if you run this show controller NPU stats VOQ ingress command, again, keep in mind this is your egress interface, port 0, and this is your ingress line card. So what we see the traffic hitting these traffic classes, traffic class 0, traffic class 5, 6, and 7. And currently we are not seeing any drop. So the credit request mechanism comes in, and since we have the packet sitting in the highest priority queue, first that queue will be served, and the credits will be granted to the priority queue first, P1 priority queue. Once that queue is emptied, then we'll go to the P2. One credit at a time. You remember the round robin fashion. One credit grant to P2 in this NPU, and then one credit grant to P2 on this particular NPU. So once we have emptied the P2 queue, then it comes down to normal priority queue. And the credit grant, credit request mechanism work in the round robin fashion with the same priority, one packet at a time from each queue, as you can see, from 3 to 2 and 2 to 1. And that's that's how it drains out the incoming traffic from the ingress queues. So that's a pretty simplistic view of how the credit grant, credit request comes in. Credit request and credit grant mechanism works when we have the traffic in the incoming queue. So let's see what we support, and then we'll dive into on the egress side of the QoS policy and how that works out. So in an MQC scheduling and action support criteria, what is supported, what is not supported, right? So if we have an MCQ configured, if we have a priority class which is not supported on the parent level, but rather you can configure on the child level. On the parent level, only the class default is supported. Shaping is supported at the parent level, and then bandwidth, as we all know, the bandwidth is not supported. Bandwidth remaining ratio, which we will today talk about and understand how that works, is not supported on the parent level, but rather you can configure that at the child level. Queue limit is not supported at the parent level, but it's supported at the child level. And red, which is not supported at the parent, but is supported at the child level of the QoS policy. So this is kind of our demo setup, where we have a router with two line cards, 02 and 06. 06 is our outgoing line card, and 02 is our incoming line card. We will take two interfaces from the incoming line card and one egress outgoing interface, and we'll see how that works out. But before we do that, let's run some of the commands. Let's understand some of the commands and what it gives us. So show control NPU VOQ usage interface, and this is our incoming interface. What we are trying to see here is the VOQ base 6560, and this is also incoming interface 02037, and 7232 is our VOQ base. This is based on the NPU 1, and this particular interface is based on the NPU 0 of the line card. If you look at the egress line card, the VOQ base is 19,784, and it is residing on the NPU 3. So all this information we can see from different commands as well, but as of now, let's have a baseline. One thing, if you notice here, we are running this outgoing interface, but on an outgoing line card as well. Usually what we do is we have an outgoing interface and incoming line card or ingress line card. But if you remember from the last discussion, the VOQ IDs are same for each interface on all the ingress line cards and ingress NPUs. So for a given interface, for a given outgoing interface, egress interface, the VOQ IDs are exactly the same. We can run some of the commands and we'll show you that, and how the scheduler differentiate between which VOQ to serve if the same ID is assigned to each to one VOQ. For example, take a VOQ 0 for this particular interface on all incoming line cards. It will be 19,784, but the VSC will differentiate that. VSC is different for each outgoing or egress interface, and VOQ, that particular queue, VSC will be unique. And we'll look at some of the show.
Mohammed, quick question. Can I ask you a quick question? So the outputs which you showed, is there any corresponding configuration, or are you going to cover next?
There is no corresponding configuration as of now. This is as without the QS configuration, but we'll talk about the QS configuration now.
All right. Okay, thank you.
Like I said, these VOQs are always there, right? Without any configuration, these are there as an architecture of the ASIC and the VOQ, based on the VOQ architecture. These queues are always there. So if we see two incoming interfaces, and when we see no oversubscription case, so keep in mind we have 7 traffic classes. Sorry. P1, P2, and then we have normal priority classes where we have assigned the weight 1, or by default the weight will be 1, right? So this is 100 gig 02, 024, 02, 037. And if we send 100 gig line rate traffic, and since there is no congestion, there is no traffic coming in, there is no congestion. This is outgoing interface is also 100 gig. There is no need to migrate or evict the VOQs to the HBM. It just works this simple way. So incoming goes to the fabric as the lack of packet we might have seen earlier, and it goes to the outgoing interface. But when we have the oversubscription case, what happens then? As maroon or red color, actually, this is the DSCP 0 marked as the traffic class 0. If you send 100 gig here, 100 gig here, since it's the same priority, so one credit request, as we saw in the beginning, actually, one grant to this NPU or one credit grant to this NPU, so one at a time. So one packet from here, one packet from here. So it means that half of the traffic or available bandwidth will be taken by this traffic and half will be taken by this traffic. So this is pretty simplistic scenario here, 50 gig from here, 50 gig from here. But what if we change the QS policy? Then what happens? This is the simplistic view where you have either no policy or you have the default policy. So if we change the policy, then what happens? Before we go there, let's try to understand a couple of these commands, right? So if you run this show controller NPU debug shell 0, remember this is the NPU. This is for this particular interface, which was on NPU 0. And this is the keyword, script read dynamic VOQ QSM location 02. That's your ingress. So what we are seeing here, number of buffers, how many buffers are being used. So keep in mind 12,208. We'll come back to this calculation why 12,208 buffers are used, but based on our configuration, which will come later on, actually, I'll show you. The number of buffers needed in HBM are 12,208. This is your VOQ ID, 19,784. And number of the non-empty queues is 1, which is shown here. Means that this is the non-empty queue where we have the traffic. If you have more non-empty queues, those will be shown here. If I run this command on a router now, which actually I tried, there was no output because I do not have on my router. There is no traffic, and I don't have any non-empty queues. So if you don't have non-empty queue, you won't get any output here. So similar situation here. This is for this particular interface, which is on NPU 1. That's the only difference, 0 and 1. Rest, we'll revisit this one in a few minutes. But what it shows is number of buffers or number of buffers being used within HBM. So now, if we have a case, earlier we had a case where the same priority traffic was coming on this NPU and on this NPU. But now, what we did is we send a high priority traffic with the DSCP 6 marking on this NPU 1, and on NPU 0 we still have the default priority or with the traffic class 0. Now what happened? Of course, as we know that the highest priority queue will be serviced first, and since we are running the line rate, we are sending the line rate, there will be no traffic will be passed from NPU 0, or we can say the DSCP 0, but rather this high priority traffic will be given the precedence, and again, the credit request, credit granting mechanism will be busy emptying this queue until it does empty, and since we are sending the line rate traffic, it will keep servicing this high priority queue. These are the commands. Show policy interface. This is your input interface, 02024, 0237. And if you see this particular command, which is very useful, this is again your outgoing interface. What we are seeing here on traffic class 0, we are seeing all the drops. Whatever packets we are receiving, we are dropping all the packets. But on traffic class 6, for this output, if we see whatever we are receiving, we are transmitting all those packets, and there is no drop packet in there. So actually, I was working with one of the customer setup customer issue yesterday, and this command was very useful to identify that where we are seeing a traffic drop and why we were seeing we had to run some of those commands. But point is, this command is very useful even in the production kind of scenarios where we are trying to find out that what packets are being dropped and why, and which queue is being actually dropping the packet. So this is just a traffic generated snapshot that the traffic with the DHCP 6 marking or traffic class 6 is being sent 100%, and there's all the traffic is being dropped for traffic class 0. Now, we can make it a little more interesting scenario here. When we do not have any priority queue or priority traffic, there's no P1, P2, but rather we have the normal priority queues. But in our case right now, we do not have a similar weight assigned to each non-priority queue. So in our case, we have for traffic class 0, we have weight 20 assigned, then weight 30, 35, 40, 50, and 60. And this is where we will try to understand that how this weight criteria works and how the packets are being serviced. So now we are sending the traffic with DHCP 0 and DHCP 5. So if we see DHCP 020 and DHCP 5, so it means 3 to 1 ratio if you see that. So 60-20, that's 3 to 1 ratio, right? So 3 times more traffic will be serviced when the traffic comes with the DHCP value 5. So as we see, we have 100 gig interface as an outgoing interface. We are pumping the line rate traffic on the incoming interfaces with the DHCP 0 value and DHCP 5 value. But since the weight is assigned is 60, we will take 60 versus 20. So we will take this 3 times more traffic for DHCP 5 versus the DHCP 0. So 75 gig versus 25 gig. The rest of the traffic, of course, being dropped. We will get the 100 gig outgoing interface traffic. So this is a slide where we will spend some of the time and see how this all works out and try to understand the bandwidth remaining ratio as well, right? So let's go through this output first. First of all, let's try to understand what is the policy. So traffic class 7. In our case, we are sending the priority traffic as well, but we are limiting it to 1 gigabits per second. In earlier example, we were not sending any traffic. So just to make a simplistic view of 75 and 25, 3:1 ratio, but now we are making it a little bit more complicated here. So we are sending the priority class traffic as well, P1 and P2, but we are shaping it at 1 gig each. Priority level 1, priority level 2. Then we are having the queue limit of 75 megabytes, which is constant across all the classes. But if we look at traffic class 5, 4, 3, 2, and 1, we are assigning the bandwidth remaining ratio 60, 50, 40, 35, 30, and 20, which we saw in the previous slide. Now, how the traffic distribution happens, keep in mind we have 100 gig interface. So 1 gig and 1 gig, each gone to traffic class 7 and traffic class 6 means that priority class 1 and priority Q1 and priority Q2. Now we have 98 gig of the remaining bandwidth. How that 98 gig is translated to 60, 50, 40, 30, 35, and 20. Let's try to figure it out, right? First of all, this is show QoS interface output command, a pretty and regular command. It shows you the base VOQ 19784, which will be your traffic class 0 queue right here, 19784, and then add on top of 1, offset 1, offset 2, offset 3, so 19787 and so on, 788, 789, 790, and 791. So your base, which is your VOQ ID is base plus offset. So offset is 0 here, 1, 2, and 3. That's first thing. Second, we have configured the shape here, 1 gig, 1 gig. That's pretty self-explanatory because we have configured that such way. But now if we come to the traffic class 5, what we are getting, that's 25 gig. Then we have 20 gig, we have 16.6 gigs and 14.5 and 12.5 and 8.3 gigs. How that comes down to. Let me find out the calculator here and try to explain that, how that works out. So remember, we had 98 gig remaining, right? So that's where this comes down to an interesting scenario. So let's say this is 6, 5, 4, 3.5, 3, and 2, if we simplify that way. So 6 plus 5, 11, 15, and then 20, 23.5. So if we take this as a number, so 6 versus 5 versus 4 versus 3.5, if we add all that, that's 23.5. Now we have 98 gig divided by 23.5. That's your 1x, 4.17. Now, if you see this is 2x. Multiply that with 2, 8.34 gig right here, 8.34 gig. Divide with 2, multiply with, let's say, 3.5, which is your traffic class 2. Let's go traffic class 2, 14.5, 14.595, exact same number, 4 until 4.4. So as you can see, that's how you, this bandwidth is assigned. Remaining bandwidth, and you come up with this is my simplistic way of finding out how the system calculates this bandwidth. You can come up with your own formula, but I thought that this is the easiest way. You add these numbers, divide total bandwidth with that, come up with 1x, and then whatever x number, this is 3.5x, 4x, 5x, and 6x, and so on. So 3.5 divided, this is 1x multiplied by 6, that comes down to 25.02. It's right here, 25.02 until 76, right? So I thought this is interesting to understand that how this math works out. Any question here? Okay, so things like this is pretty straightforward. Now let's go back to the Q limit, right? So Q limit is 75 megabytes. This is again hard coded kind of way. But how this comes down to 600 milliseconds and 24 milliseconds and then 29 milliseconds? That again it's the way it is. If you take the bandwidth, let's take this particular bandwidth, right? That's your kbps. If you convert that into this is your 1 millisecond. Divide that with, multiply that with 8. That will be your bytes, and then divide that with your with 1,000. That will give you 1 millisecond, and then multiply with 41. You will come up with exact this number. Or you can do the reverse math. I have done that, so I'm just trying to save time. The way we did the math exactly is if you do the math for the Q limit, it will comes down to the pretty exact numbers, actually 600 milliseconds to 24 milliseconds to 48 milliseconds, 41 milliseconds, and so on. Moving forward. So bandwidth remaining ratio, as we took this example earlier, from the traffic generator snapshot, it shows you 75 versus 25 gigs. And if you run the show commands, that's also gives you the about 75 gig and 25 gig. The reason it's not exactly 75 gig, we'll come to that in a few minutes, but hardware programming is hardware programs in a certain way, certain numbers, incremental or decremental with a certain number, does not implement one at a time. So it chooses the nearest number. And that has been in some of the other platforms as well in the past. So now if we come down to this 12,208 actually, if you remember, 6 kilobytes was or is the data HBM1 block stores, right? So 6 kilobytes multiplied by 12,208. Let's say if we do that math, that's 1 kilobyte, 6, 12,208. That's your 75 meg. Yep. That's your Q limit. So that's where I was mentioning earlier that this is also relative to our configuration. And of course, if you increase the buffer size, actually, or you increase the shape limit, in our case, it's 10 gigabits per second. It will change the buffer size as well. Now, if we talk about the red, how that works out with the shaper, actually, we'll come to that. But so far, if there's any question, what we discussed so far, we'll take that question and then we'll move to the random early detect section. Okay, so let's move to next section, random early detect. So if we have a policy with the shape 10 gigabits and then random detect 100 megabytes to 200 megabytes, keep in mind, again, a reminder, WRED is not supported on this platform, and that is being kind of worked around with the upper limit and the lower Q limit. Now, how that works out, let's look at that. So first of all, we have 10 gig, and we are sending 10.5 gig. But we are receiving 9.5 gig. Again, that comes down to the programming of the hardware. Let me just flash that slide right here. If you run this command, show controller NPU debug shell 0, and then run this script, that tells you that the peak information rate is 9.6 gig. That's how the hardware programs that. And in order to get to that rate, how many buffers you need? 24,416, 412. And then the rest of the information, what slides this interface is on and all that. So what is, how random detect work on this platform, right? So this ASIC actually, Pacific ASIC supports the random early detect based on the condition management for the VOQ in the HBM. There is one curve supported, and what that means that we do not, or we cannot set the different threshold for different stream in the same VOQ. There are 8 regions, and we'll talk about that region, but there are eight regions. We have divided this queue when we configure the random early detect. And there is a threshold, there are 8 thresholds, or each region has a particular threshold of the traffic drop. Let's go to that right here. If we see, if our incoming traffic rate is until 9.6, since the hardware has the capacity of programming exactly 9.6, the probability of the drop is 0. But as you move forward from that traffic rate, your probability of the traffic drop is start increasing. That's about 14%, 28%. So you come up with this linear curve here. This is a formula. Without going into that formula detail, if you configure such that if you increase the traffic, incoming traffic, your probability of dropping the traffic is increasing until about 67 gig if you are talking about the 10 gig interface. After 67 gig, all the traffic, because you have filled up your queue from all 8 regions, all the traffic will be dropped randomly. But if you configure the ECN, it will mark the ECN bit actually in the traffic. So some of the commands actually, I think we talked about that earlier. And we also talked about the remote versus the local part of it. If your interface, outgoing interface is on the same line card, it will show it as a local. If your outgoing interface is on a different line card than VOQ you are looking at, it will show you as remote. So some of the steps actually for the drop debugging. So where is our packet is being dropped? First of all, we need to check that what is happening on the PDVOQ state in the MP pipeline. Then we check the ingress traffic is being sent to the correct VOQ. How we can check that? We can go back to some of these commands again. Let me just go through. So this shows you correct traffic is hitting the correct VOQ. So this is one of those commands. Like I said earlier, this is pretty useful command. Pretty simple but useful command. And then check the destination system port to the VOQ mapping. Usually this is pretty correct, but due to some software bug, this could be messed up as well. But we haven't seen anything so far. Check if the RxPP has determined the correct forwarding destination port, so maybe the programming of the forwarding port is not correct and so on. There is a wiki actually which gives you all these details with the show commands and some of the example outputs. So I would highly encourage to go and check that wiki out.
So Mohammed, a quick question. So what you are suggesting is, if do we have to like follow these steps, what you showed to while debugging? Because a lot of time when we want to.
These are not the serial steps. Let's put it that way. Depending upon what you know about the situation or about the traffic drop or about the issue,
Right.
actually you can start from there. But
Right.
these are the general guidelines for not specific of number 1, 2, and 3 kind of.
So other than checking the show commands, do we have any like a traces or something which you think we should go check?
Yep, we do have right here, show QoS EA traces, show OFA traces, and then we have a couple of show tags as well. This is PI show tag and then PD show tag. And then on the systems, we do have these logs as well.
Right. So is there any like typical, error messages in the traces we should be looking for, like a keyword or something? It is because it is very difficult to go through traces. If we have certain keywords, it will be easier to look for those, Of course, each issue is different, but generalizing, if we have certain keywords, it will be easier to look for those keywords.
Yeah, so keywords are generally speaking, it's the error keyword, unavailable keyword, or misprogrammed. Maybe that's what I would be looking for. But there is no specific guideline. Again, go through that. This wiki, it has discussed certain scenarios where if you see a kind of traffic drop, what to expect in what command, kind of that scenario, right? Today, we are not going to go into that deep dive of troubleshooting. Sure. We are trying to understand how what QoS works and all that. But in the future, if there is enough interest, probably we can deep dive into the troubleshooting part as well.
Okay, thank you.
Yep. So let's take the example of this.
I have one question over here. So for the slides on QoS on Spitfire, it's based on layer 2 package size or layer 3 package size?
Layer 2.
Layer 2, okay, thanks.
Okay, so here's the thing, right? I have this system, and what is running 731. It's not my own system, so I don't know about the traffic, but this is a D12 chassis, 8812, and we do have two line cards, 48 and 36, and as we know that 48 having 2 NPUs, and then 36 by 40 gig have 4 NPUs on that line card. So if we run some of these commands, we work with, right? So let's take a 40 gig interface here, and then instance all location at incoming line card is 00. Let's say different line card. So that gives you the VOQ, show controller, and PU, VOQ, interface all, instance all, location all. So that gives you the complete information about the system. Now, if you go this and see this, check this out, since we have just 2 line cards, actually, it will be easier. So it tells you that what is the base VOQ for this interface, because this particular interface, even though it's on the same line card, or different line card in our case, but let's take 0500. So 0500, incoming interface and outgoing interface are on the same line card, but 14,528, right? So if we take that one, 14,528, and then go to this online card, it should have the same VOQ, right? So this is the same ID, same VOQ ID for this particular interface on this line card and this line card. So that does not change. What changes VSC? So VSC is unique per connection. All right, so definitely we can run some of the other commands, but since I do not have any traffic, I'll, for example, take this command, right? Let's go back. Take this command, copy this location 00. Since I don't have any non-empty queues, it says there is number of non-empty queues 0, so it does not give you any output. So the same goes for line card 5 as well. So this is expected, just in case if somebody is trying to run these commands and expecting the similar kind of output. You don't have traffic and you don't have probably QoS as well, but definitely no traffic. Okay, so let's move to this section of the classification and marking. So today, actually, what we learned, just as a summary, right? So we learned about the VOQ architecture, how the credit request and credit grant mechanism work, some of the show commands to see how the traffic flows and what kind of programming we can see, like the VOQ and all that. And then we apply ingress and egress QoS policy. We saw if we configure the bandwidth remaining ratio, how the traffic is being distributed among different queues and all, right? Of course, we understood the HBM and SMS architecture as well. But what we have not talked about is the classification and marking, and then the policing. Policing section, we may or may not be able to get to that, but we'll see if we can get to that today. But we'll talk about the classification and marking and try to understand that what kind of classification and marking mechanism we support and how it works out. So first and foremost, there is two kinds of classification supported. One is the map based on the map, hardware map, and one is based on the TCAM. So what is the difference? When a policy is matching only on the simple scenario like the DSCP or precedence value, the system selects the map-based classification system. So map-based classification system, when the matching criteria is the simple matching criteria based on the DSCP and the precedence value, system will select. And by the way, the user do not have to select one or two, or one or the other. What you are matching on, that will decide, that configuration will decide that what classification criteria we are using. So if we are matching in the DSCP and precedence value, it will select the map-based classification, and anything more complicated, for example, match on ACL and so on and so forth, that will take the TCAM into consideration. On the ingress side, we support the QS mapping. We support the map and the TCAM both. And on the egress side, we only support the map-based classification. So result of this classification, once we classify the traffic, what can we do? We can do the marking, we can do the policing, we can do queuing, and the counter selection. One important point here is if we have a policy which is matching on DSCP as well as some complicated matching scenario, let's take the example again, ACL. If we have mix of both, in that case, actually TCAM will be used for the complete policy. It won't be like the part where we are matching the DSCP will go to the map-based classification, and the matching criteria where we are matching on the ACL will go on TCAM. No, it will completely use the TCAM for the whole policy. There is no mix of table and TCAM classification. And this table shows us that based on what packet type, what we support. So we support pretty much everything except the MPLS EXP. On the ingress side, we cannot have the TCAM matching. So this again describes what is the ingress classification criteria. We can use the IP address, source and destination IP address. We can use the precedence value, DSCP value, and MPLS EXP value based on the protocol, or what port, what port TCP, based on the TCP flags and ICMP type and the code. And these are the, we can classify based on that. And then how we can match on the ingress side, we can use the ACL, we can match on DSCP, MPLS EXP, IPv4, v6 precedence, and then match on the protocol as well. So as I mentioned, that software automatically select the hardware table or the TCAM based on the rules we have described in the policy. So simple classification rules again uses the QS mapping table, and more complex classification use the TCAM. And by the way, on the on the fixed platform, there is no TCAM classification, only map-based classification is supported. So on the egress side, there's no TCAM-based classification on the egress side, as we mentioned earlier. Only the hardware-based classification is supported on the egress side. So there are two tables maintained, one for the MPLS table, one for the IP table, and these tables are for NPU. So if you have two NPUs, so each NPU will have IP table and the MPLS table, and the NPUs do not share these classification tables. So on the egress side, what we support the DSCP, precedence, MPLS EXP classification. Sorry, I keep moving that. And we match on the QoS group, we match on the traffic class, And traffic class is strictly for the queuing policy only. So like we saw the example earlier, we were setting the traffic class on the ingress where we were matching on the DSCP. So if you remember that example, we looked at the ingress policy was matching on the DSCP value, setting the traffic class, and then on the egress side, we were classifying based on the traffic class and performing certain actions like the priority, shape, or bandwidth remaining ratio. But shape and bandwidth remaining ratio, for example, these are the queuing mechanism. So in order to use them, you have to match on the traffic class on the egress side. So for the egress classification, we can match on the QoS group 1 to 7. So match on the QoS group 0 cannot be configured because that is strictly used for the default class. So mix and match classes with the DSCP and MPLS EXP in a policy is supported, but you cannot do that with the QoS group. Means that if you are matching with the QoS group, then you cannot match with the DSCP or the MPLS EXP in the same policy. So when there is a match with the QoS group in the policy, you cannot have the other matching type. So you have to match only on the QoS group type. So there is no egress classification on ACL on layer 2, and match not, that keyword match not is not supported with the match QoS group or the match traffic class. So you cannot have a classification criteria that match not on QoS group 0 or QoS group or traffic class 0, for example. So if we have an IPv4 or IPv6 packet type, what is supported on the ingress side? I think this is a summary from the previous discussion, but this is a kind of summary slide instead of text slide. Actually, this table need to be put it on the bookmark or probably print out and put it in the cube just to better understand what is supported on the ingress and the egress side when it comes to the classification. On the remarking side, on the ingress L3 marking supports, what it supports, we can set the QoS group on the ingress side, we can set the traffic class on the ingress side, and of course we can set the MPLS EXP in position, the DSCP value, and the precedence value. On the egress side, we can set the MPLS EXP topmost, we can set the DSCP value, precedence value, and then we can set the cost value. But this is for the L3 sub interfaces. Some of the show commands, again, these are pretty common show commands, but if we have a policy where we are setting the DSCP AF11, for example, here and AF21, show QoS policy will tell us that, or we can see if it is programmed correctly. Of course, if this is converted, AF11 is converted into the decimal format here. That's the, I believe has a format here. So I skipped through a slide. It's pretty straightforward. Again, this is the DSCP marking, but in-place modification is supported or not. So we do support the in-place modification for the classification policy. So this modification is supported, and how we can do that? We can modify the policy map itself. We can modify the class map itself, or we can modify the ACL, which is used in the class map within the QoS policy. So we can modify anything on the fly, but as we all know that while we are committing that, it actually removes and reapply the policy. So we have to keep that in mind in the production environment where we have the strict SLAs and so on, right? So there might be a time that when you do the in-place modification, it takes time to reapply the policy after removing it. So keeping in mind. But again, this is not specific to Spitfire QoS. So we can modify the, once we modify the policy map and the class map, it will reset the stats. So that's also another consideration actually. A lot of time, customers actually rely, or their tools rely on these stats. So once we modify these policies, it will reset their stats as well. So during the policy modification, we need the extra hardware resources, maybe depending upon what we are changing based on the old and the new policy, and that's where sometimes it is possible that what we are trying to change that it will fail due to the out of the resources error as well. So how to debug the classification and marking? So we need to check the interface stats, forwarding stats, check the control plane if the policy is attached in the correct direction. In most cases, actually, since we have a limitation that what is supported on the ingress and egress, we might not run into this scenario on Spitfire platform. For example, if you are trying to have a policing configured on the egress, it's not even going to commit that, right? So it will give you a pretty clear error that this action is not supported. But again, it's important that we understand that where we are applying a policy, and we need to check the control plane stats as well, which is the couple of show commands, show QoS, show policy map stats command will give you the control plane and the data plane stats. So again, these are the forwarding stats show commands, straightforward show commands, nothing new in there. So in order to check the control plane, if it is connected in the or attached with the on the correct direction, actually in the correct direction, that's the command we need to check. Control plane starts with the show policy map output. So this is a very common command we run into, but it's very, very important command as well because it gives you a lot of information. If we haven't noticed that, it gives us the QID as well, it gives us the tail drop as well. So a lot of time actually with one command, you can actually figure it out what exactly is happening. So if you are having the tail drop, you can check that tail drop, and then of course using that particular QID, you can run view queue related command and see check over there as well. But generally speaking, sorry, my mouse keeps moving. Generally speaking, this command gives you a lot more information than usually what we think of. And if we pay close attention, we can figure out a lot of things with a couple of these commands output. They show policy map and show QoS interface command. Now, if we check the data plane, if the policy is correctly configured, so we configured a policy. In our case, let's take the example here. We are permitting the TCP traffic from any network to this particular host, which is the www traffic, right? So if we, first of all, show IMD interface manager database, we get this ID interface handle, and then use that to get another information. I don't exactly remember on top of my mind that what exactly this call is, but take this information and run this show controller and view debug shell script command, right? This gives you the programming in the hardware. So IPv4 destination, yep, IPv4 destination, right? What is the IPv4 destination? What is the protocol? Yeah. Sorry about that. So what is the protocol we are using? What is the destination port we are using? If we convert that hexadecimal into, this will come down to 80. So this gives you the detailed information about the programming in the data plane.
Hi, Mohammed. Is that output is specific to your platform, or is that layout is maintained for every other platform too? Is the same for any other platform too? My question is what are the platform programming? This layout is it same for other platforms as well?
Yeah, no, actually, I started talking and did not realize I was on mute, so I actually gave the answer, but I did not realize I was on mute. So these scripts are, I'm not sure if these scripts are available exactly on the other platform. I don't think so, right? So if anybody is aware of these scripts are available on this Predator platform, please speak up, let us know as well. But these might be specific to the Spitfire platform.
Okay.
Because keep in mind that the ASIC, right? So internal ASIC versus external ASIC, Cisco only ASIC versus the Broadcom ASIC. So there is a limitation on what you can run.
Okay.
Make sense?
Yeah, thanks.
Okay, so that actually brings us to the conclusion of the marking classification and the marking part of it mostly. As you can see that some of these show commands are pretty useful in checking what we have configured is exactly what has programmed in the hardware. Having said that, actually, we have QoS wiki pages, which are mentioned earlier, as well as they are part of the one-stop shop as well. So please feel free to go and check some of those show commands and output and try to understand more what exactly we would be or we should be looking if we are expecting that we have configured a QoS policy, but it actually is not working, even though the regular show commands are showing it is programmed as it is, but in the data plane, if it is correctly programmed or not. Some of those commands will be very helpful. So we are almost on time, actually. I'm thinking if we can start this policy section, what we can do is we can take a start, but we most likely will not be able to finish it up. So here's what I would suggest you guys, right? Instead of just rushing through these few slides, if you guys are okay, like I mentioned this earlier, this one-stop shop, let me paste that again on the chat window. Okay, somebody did mention
Mohammed,
that
just quick thing. Just now I see the pop-up on the chat window from who is this?
Yep, I saw that. Yeah. So there's one command, DPA L3 interface show client is will be depreciated, and there will be a new command actually. So I will update my slides with that. Let me just copy paste this somewhere.
Okay, thank you.
I'll take this one and I'll update the slides and we'll mention that. By the way, do you know that what release this will be depreciated if we have that information handy? And if not, it's okay. But if we do, we can actually put that in the slide as well. So coming to this one-stop shop, right here, QoS section. So we have a lot of information here. So instead of just rushing through the slides, I would like to see that if we can stop here. And these three sections are actually presented by myself and exactly the same slide deck, where we used our own time and took three different sessions. Last section is probably related to the policing mostly. The first one is the VOQ architecture. Second one is the marking and the classification. And the last one is policing. So there is a recording available, as well as this section is from the development team. So they actually provided this TOI way before me, and I used their slide decks actually to come up with my own slides. So nothing actually is new here, but rather I just collected a lot of information and put that in one slide deck, which is about 120 slides. So these recordings are very, very helpful if you guys would like to revisit them. And then if you have any questions, definitely do ask those questions. Well, if there is interest, like earlier there were questions about the troubleshooting part of it, we can come back with one quick session of 1 hour with the troubleshooting, and I'll try to get a router with the actual traffic running on it, and we'll see if we can modify some of the configuration as well, and we'll run some of those show commands related to the troubleshooting part of it. So having said that, Akhilesh, I think I'll stop here and we'll take any questions or comments. But policing part of it, like I said, we have 2 recordings available, and it's a huge section, by the way. And there are a lot of new things in the policing section, like 2-rate 3-pillar is not supported and why it is not supported, and all that good detail in the recording as well as in the slides. So please go through and let us know if we can actually have any troubleshooting section in the future. If no question, Akhilesh, back to you.
Hey, Mohammed, thank you so much. Very good session, and really appreciate your continuous 3 sessions. One is on BGP flow spec and then on the cost. All these session recording and material guys will be available on Joy of Learning portal also. Today's recording will also be uploaded tomorrow. Please feel free to ask any question. Otherwise, we are on time.
So I have a question here. So for the policing, do we support any other than like a user configured policer? Do we support any internally configured policer? like policing the traffic going to the control plane?
That's LPTS, right? I mean, if you're talking about the control plane policing,
Right.
is that what you're asking?
Yes. Is
So
that going
that
through
is
the
not
same
related to
mechanism or it's different?
No, that we are talking about the user configured policing right here. So that LPTS has predefined policer for different kind of traffic or control packets. So if you run some of those actual LPTS commands, actually it will give you that policer rate. And generally speaking, we don't change those configurations. No customer has actually ever, probably in my opinion, has changed those configurations. Maybe where there are very rare cases, but those are related to the LPTS policing when it comes down to the control plane policing. That has nothing to do with our user configured policing here, what we are talking about.
Okay. One more question, if I may. So can you comment on the scales of the QS? Talk about in terms of how many queues do we support? How many policers do we support? Do you have those numbers?
Policer part, right? So policer part, first I'll address that. So policer part, again, there's a lot more detail in the slides. For the queue, how much queues we use and, what's the scale number? We touched upon that last time, and that there is a limitation on the scale, how many classes we can use, how many per policy map, how many policy maps we can use. And there is enhancement, or there is a change coming up where from 8 class maps to 32 class maps will be supported in a certain release. So that has been addressed. But again, there is probably a scale document as well. Let me check if I do have that here. Yep. So there is a scale section of on this one-stop shop. It might not have exact what you are looking for from the QS point of view, but in general, related to a particular release, we do have the scale-related information there. So if you are looking for specific to how many sub-interfaces we can have with a certain policy, that comes down to, again, the limitation of the BOQ architecture, that how much we can use that. So briefly, we touched upon that topic actually last time. But again, there should be a scale document which can be asked from the test teams, but that's not the part of the TOI in general.
Okay, thanks.
Sure. Okay, thank you. Thank you again for joining.
Thank you. Thank you so much, folks. We are closing.
Thank you.
Thanks.